Yeah, so I'm Srinivasan Raghunathan. I'm also a CAPS fellow like Cynthia. This is my second year. And I'm going to talk about the kinematic Srinivasan effect. So this is basically what I do. So I try to find new estimators and new methods to analyze data, mostly working on cosmic microwave background experiments, mainly South Pole Telescope and CMB-S4. Pretty much everything that I'm going to show is based on the paper that was out like earlier this week. All right. Okay. So a very brief introduction to the universe. Right. So we are cosmologists. So we try to model how the universe started and how it evolved. And this is what we believe at Appen. And we have pretty much very good evidence for most of these things, but we are still searching evidence for example, inflation. So here's a picture. So first, we believe that there was inflation. So that's cosmic inflation, followed by Big Bang. Okay, so if someone asks you why did the Big Bang happen, so it's because of inflation. Right? So we are trying to find why. I mean. We have a very good model, but we are still trying to find evidence for this mathematical model. And then, so that's basically the start of, let's say, time for our universe. And then over time, universe is expanding, right? So it started from a really small point, and then it started to expand. And as it expanded, it started to cool. And roughly 400,000 years after the Big Bang had happened, we see this thing called the cosmic microwave background. So this is the farthest thing that we will ever see. We can never see beyond this. So you look at any direction, you see cosmic microwave background. So that's the edge, right? So that's really the edge that we can actually see, because beyond that, universe is very hot and very dense. So photons can never travel through that very opaque medium. And then over time, so universe expanded further, and as it cooled, it started to form stars, galaxies, structures, everything that we see today. Okay. So how did it form structures? So it's a hierarchical structure growth. So basically, smaller structures formed, and they combine to form bigger structures. And then when we talk about gravity, it's very well explained by general relativity. People are trying to find evidence to go beyond GR, but so far GR seems to explain everything pretty well. And then the universe that we live is very flat. Observations suggest all these things. Okay, so this is basically my field of work. So cosmic microwave background. So like I said, so this is the radiation from the Big Bang. Okay, so when you say Big Bang, so this is really what we talk about. So it's a remnant radiation from the Big Bang. It was predicted in 1940s, and was actually serendipitously discovered by these two people in 1960. Okay, and they won a Nobel Prize for that. So this radiation is very, very homogeneous, and it's isotropic, meaning any direction you look, this radiation is going to be the same, like everywhere that you see. There are really small anisotropies on that very smooth background, because if those are not there, we are not going to be here today. Okay, so it's because of that structures formed, and because of that we are here, right? So we call it this black body radiation, and it peaks at around 2.7 Kelvin. So this is really the temperature of our universe. So it's 2.7 Kelvin. So it's negative 270 degrees Celsius, right? And then this radiation. So we are mostly talking about temperature here, but this radiation is also polarized, roughly 10%. And then since this is basically beyond everything that we see, and then structures formed later. So this radiation is going to be influenced by everything that we see in the universe. So basically galaxies, clusters, everything. It's only a very small fraction of the CMB photons, but it gives rise to very, very rich science that we can actually do with this radiation, right? So that thing, it gives to numerous secondary CMB science that many of us in this room do. So I'm going to focus on the Srinivasan effect, but then there is lensing, like Kale is working on lensing from SPT, and like there are like so many things that we can do with these things. Okay. So South Pole Telescope. This is the telescope that I primarily work on. I'm with many people here. It's a very beautiful photo took by one of the winter rovers last year. Picture of a lunar eclipse. It's just so amazing. So obviously this is in South Pole, Antarctica. This telescope is 10 meters in diameter, so it's really big. One of the biggest cosmic microwave background experiments. So the bigger the telescope is, the finer the resolution is, so you can actually see smaller and smaller structures, right? Because you can collect more and more photons. So just to give a comparison of how good South Pole Telescope data is. So this, for example, might look like nice, but this is actually cosmic microwave background. So this is a map of the cosmic microwave background from Planck. So Planck is the satellite that observed microwave background for 5 years. I think it ended in 2013. So this is a map of Planck, unfiltered. This is basically after doing some filtering. So you see that there are these things. So these are basically, so the background is cosmic microwave background. And then on top of that, you see these sources. So these are actually galaxies, okay? So these are galaxies emitting pretty much in the same frequency that we are observing CMB at. But if you take the same location, and if you observe that with South Pole Telescope, so you see how good this becomes, right? So this is like a very, very fuzzy image of our sky, and in the millimeter wave. It's basically the same region, but it's South Pole Telescope. So you see now you see like lots of those points, right? So these are all galaxies, right? So we call them point sources because they are just point-like for us. So you can actually see that these are all point sources. So these are all galaxies emitting in millimeter wave, and this is actual data. And these points are coming from the point source catalog that Melanie produced, right? So this is real data. But more than this, you also have these black dots. It's kind of hard to see, but you see the white dots are galaxies, and then you see black dots. So these black dots are actually galaxy clusters, right? So these are groups of galaxies. And in cosmic microwave background, at 150 gigahertz, they appear as a shadow. They appear as a decrement. I can tell why that is, but it's probably too much detail, so I'll just skip that. Like people like Felipe, for example, has worked on a lot of these things. So he worked on ACT with looking at these kinds of objects. So it's amazing. So the data set is amazing. So you can do a lot of small scale science, right? So the secondary science. So.
Stupid question.
Yeah.
Was the frequency difference important there, or is it just that the telescope has better detectors overall?
It's basically the telescope has better detectors, and it's also bigger.
Okay, so it's not the difference in 140 and 150.
No, it's not that. Yeah. And all these telescopes, they observe in multiple frequency bands. I just showed 150 because 150 is a pretty nice band for CMB. But South Pole Telescope observes in 3 bands, Planck observed in 8 bands, and the future telescopes, they observe in like 6 or 7 bands, depending on the science they want to do. Okay, so these are the maps. So this is really how our sky looks in millimeter wave. But we are cosmologists, so we don't just look at the maps. What we do is we compute statistics with these maps, and you can compute the statistics in real space, which we call 2-point correlation. So basically that just says that if you see a point in the sky, can you use that information to predict how a different point in the sky will actually look? So it's basically a correlation between 2 different points on the sky. And you can plot this correlation as a function of distance from a given point, right? So you can do this in real space, or you can do this in Fourier space, which is always what we do. So this is called, so the Fourier transform of a 2-point correlation is called power spectrum, okay? So this is power spectra from SPT, from these 3 different bands. So you see 95 cross 95, 150 cross 150, and 220 cross 220. So the horizontal scale here, so that's a proxy for angular size on the sky. So if you're looking at the left, you're looking at really large angular distance. If you're looking on the right, you're looking at very, very small angular distance, okay? So So if you're looking at very large angular distance, you're actually seeing the cosmic microwave background. So that's the power spectrum of the cosmic microwave background. But if you're looking at small angular scales, you're basically just seeing those white dots and black dots that I showed in the previous plot, right? The previous slide. So those things are much brighter. So those are the things. So you can see that these are like radio galaxies, like quasars, and then dusty star-forming galaxies. So that's the SFG. And then you also have this cluster, which is like the thermal Sunyaev-Zel'dovich effect. And then you also have the kinematic Sunyaev-Zel'dovich effect. So you see that the blue dashed line, so that is basically the smallest signal in pretty much all these bands in these small scales, okay? But that signal is very, very important because it can tell us a lot about how the universe, how first stars formed in our universe, how first galaxies formed in our universe. So it's a really important signal, but it's extremely faint, and it's dominated by all the other things, so it's very hard to measure, okay?
So I have a question.
Yeah.
When you do the cross correlation for galaxies, you basically see them in every galaxy.
Right.
Compute the distance to every galaxy.
Yeah.
When you're doing a CMB map, how
Right.
do you do it? Do you actually see it in every pixel, and you move with every pixel?
You know,
You read?
we just take a Fourier transform of the map.
Okay.
So we just take a Fourier transform of the map, and then we square that. So square of the Fourier transform is the power spectrum, right? And then we basically just bin it in angular distance.
But it's map-based. So
It's map-based, yeah.
So your fundamental piece of information is going to be the size of, of the pixels on your maps.
Yeah, right. Yeah. So you cannot, for example, yeah, if your map pixel is like 1 degree, you obviously cannot look into information here, right? So yeah. So for example, so you can bin your map in however, like whatever resolution that you want, right? But it's ultimately limited by the telescope resolution as well. Yeah. Okay. All right. So then I'm gonna go into this kinematic Sunyaev-Zel'dovich effect. So what this is basically arising from two effects. So one is, so that's the cosmic microwave background. And then, like I said before, let me just go back to this plot. So that's the cosmic microwave background. Universe is evolving, so it's getting colder and colder. And then you see here, stars are forming. So stars and galaxies are forming here. So that basically gives rise to this, this signal. So when stars and galaxies are forming, so they are hot. As a result, they ionize the CMB. The CMB photons, they ionize it, so you start to see free electrons there. Okay? These free electrons interact with the CMB photons, and they give rise to this effect called the kinematic Sunyaev-Zel'dovich effect. Kinematic just means that it's moving, so electrons are moving. But then later, in the local universe, after all the galaxies and structures are formed, these halos are always constantly moving. They are moving in the line of sight, right? Because gravity is pulling things, so things are always moving in our universe. So that gives rise to this other component of the kinematic Sunyaev-Zel'dovich effect. So there are basically two sources. And unfortunately, these two sources, they look similar to us, both in like real space and in the power spectrum space. And as a result, it's very hard to disentangle between the two. So it's one of the fundamental limitations that we are currently facing to basically understand how first stars formed using this signal. Okay, so yeah, so that's basically an example. So you see this, so that's again a power spectrum. So there are three curves here. So yellow color, so that's basically the signal coming from the local universe because galaxies are constantly moving. Again, yeah.
Yeah, so I think usually we think of things being more homogeneous at high redshift and more evolved at low redshift. So how should I think about this case where you have more homogeneity at low redshift? Yeah,
very, really good question. So what that actually means is that if you're going to high redshift, right? So if stars formed in all locations of the universe at the same time, it's very homogeneous, and as a result, if that actually happened, then universe actually reionized immediately, and if that happened, then we will not even see a kinematic Sunyaev-Zel'dovich signal, right? So universe reionized in patches. So at some location there were more electrons, and some locations there were less electrons. So that's how universe actually reionized, and that's why we call it like a patchy part. But in the local universe, so yeah, so what you say is true. So it's kind of inhomogeneous, but they're basically like so many halos moving, and so the signal is almost constant everywhere. So, yeah. Right. So if you look at them in the power spectrum space, you see that there are these curves, and then these curves look pretty much the same. They are like very flat. The amplitude is also pretty much the same. So it's very hard to understand which is which. Okay. Yeah. So that's what I say. They both have roughly similar shape and similar amplitude. Okay. But why is this actually interesting? So like I said, this gives us a hint about how first stars formed in our universe. So for example, here's a simulation showing, for example, how universe reionized in 3 different ways. So people who look at these maps can immediately pick these structures. For others, it can be slightly hard. But you can see that if you look at this map and this map and this map, so you see that in this map, you basically, you don't have like small structures. So it's kind of hard to see, but if you make a Fourier transform of it, and if you look at this image, you actually see clearly that one has structures on large scales and one has structures on small scales. Right? So this is just an example. If the universe reionized this way, then you get this blue line. If it did this way, then you get the green line. Okay, so basically, if you observe this signal, you can actually say how the universe, how first stars and galaxies formed in our universe. Okay, unfortunately, so this is nice, but unfortunately, if we take the data from current experiments, basically it's only SPT who has that has measured this signal, right? So none of the other experiments have actually measured the kSZ power spectrum. So if you take SPT data point, and if you try to constrain multiple models, you see that's the data point and that's the error bar. So you see it does not constrain anything. So basically, it's consistent with all the curves that we have here. Which means the current data is not good enough to do this, to do these constraints. But like, as I'm going to show you, the future is looking really nice. Yeah.
Why do you have only one data point?
Right. So the way SPT did analysis in the previous papers is that, so they fit a template. So we assume, so for example, we take these simulations and then we have this power spectrum. So we basically fit this to our data. And then we normalize that at L of 3000. So that's why there is just one data point there. Right? But what I'm doing currently, so I'm leading another analysis in SPT, but in that case, I'm not focusing on single data point. I want to get the full power spectrum. Because it's always nice to get the full power spectrum, because if you have multiple data points here, you can actually constrain the shape of these curves really well. But current data is noisy, so it's very hard to do it. Right, so that's one thing. So the two kinematic Srinivasan signals, it's very hard to disentangle between the two. So that's one of the limitations that we have in understanding how the first stars formed from the signal. The other obvious thing is that, like I showed you before, we have these galaxies and we have all the other signals. So for example, you see that I call this CMB. So the kSZ signal is here, right? So that's the total kinematic Z signal. And then you see this red line. So that's signal from galaxies, right? So we call this CMB because it's actually like a diffuse emission from multiple galaxies. It's called the cosmic infrared background. And you see it's so high compared to this. It's more than an order of magnitude. So it's very hard to even observe this signal. Okay. Fortunately, yeah, so it's basically the same thing. So foregrounds, they're all higher than kSZ. This is basically the same plot, but showing it in a different way, basically comparing kSZ signal to these foregrounds, and you can see that for all these experiments, current and future, so current SPD and then all these future experiments, so these signals are always like more than one, right? Which means it's very hard to observe kSZ. But data from different bands can be combined in a really smart way to actually mitigate them, and that's really what we showed in this paper that was out earlier this week. And then if you do that, if you combine data from multiple bands, not just 150 gigahertz, from 6 different bands, if you do that properly, you'll get like error bars like this. So you see that's basically the error bar from the CMB S4 experiment, like doing this in multiple ways. But you see that these error bars are so small, that's the signal. So if you compute the cumulative error bar, or if you compute the cumulative signal to noise on all these scales, you get something like 60 sigma from CMB S4. So right now we have a 3 sigma measurement. The next SPD data will make that to roughly like 8 to 10 sigma. But CMB S4 can do this and like measure this at 60 sigma, which is great. Similarly, the SPD3G, when we have our full observation, when we finish our full observation, SPD3G can measure that at 30 sigma, which is great. So then we can start to do science with this signal. And right, so now here is, for example, a forecast. So this is similar to the Fisher formalism that Cynthia was talking about. So this is forecasting how first stars form. So that's basically just a proxy for that. So the horizontal axis here is basically the duration of reionization. So basically, this is a proxy for time, but shown in redshift space. But let's just say it's time. So this is basically telling us how long did the first stars take to reionize the universe. So that's basically what this axis is telling us. So you get like really nice constraints from future CMB datasets. So this is another example. So you can see that the width here, so that's basically the width. So it's plus or minus like 1.5. That's really what we get. So currently this is just unconstrained. So we have no idea about what the duration of reionization is from the current data. But you see future is amazing. And we can actually do this in this decade. Right? So SPD, for example, SPD3G plus SPD4, so that's the red one. So that can actually be done by 2030, like early 2030s, because we will have data. We'll finish SPD3G in 2 years, and then SPD4 will start. We'll take data for a few years. So basically, by the end of this decade, we will have these data in CAN, and if we do this analysis properly, we can actually get these constraints. Right? There can be some limitations, but yeah, it's really it's very promising. Yeah, so this is just the same plot, but showing multiple experiments.
Is there any remotely intuitive way you can say for somebody that barely understands these plots why this isn't just 2 error bars in 2 directions, why it's an ellipse?
Right. So it's an ellipse because these 2 things are kind of degenerate. Right. So I'm only showing these 2 parameters, but the number of parameters that I'm constraining with this given data is actually 14. So there are basically 14 parameters. So if you plot everything, it's going to be very confusing. It'll be like for example the plot that Cynthia showed with all the parameters. But I'm just focusing on these 2 parameters because these are the only ones that tell us how the first stars formed. Right. Right. Yeah. And I guess that's it. Thanks.
What goes into this? What goes into the simulations or the model templates that you're using? Is it like UV luminosity function or Lyman alpha or Lyman continuous fraction?
Right. Yeah. So basically, all of those things go in those sims, and it's kind of complicated because we don't know what actually happened. So yeah. So so the goal here is we'll observe these things and we can actually improve our sims, right? So we understand, and then it's basically like a feedback loop, right? So we want to improve our sims so we can do better and better things with these data sets. Yeah. Right.
Any final quick questions? Well, let's thank our speaker again.
Thanks, everyone.